This section will cover Control Processor 0 MT specific registers. MT registers can be broken down into three parts. Global registers, common to all MT elements, TCs and VPEs. A per TC registers that are specific to each TC, and last, per VPE registers that are specific to each VPE. This section is divided into these three parts and will cover each of these registers in detail. This first group covers the registers that are common to the whole physical processor. There is only one instance of these registers. All can be accessed by any thread in the proper mode. The multi-VPE control register provides an interface for global control and configuration of a multi-VPE. The CPA, or cache partition active bit, enables the setting of the cache allocation bits in the VPE opt register, which we will discuss later. The STLB, or share TLB bits, enable the sharing of TLBs if there are two TLBs within the 34K. The 34K allows for two separate TLBs, one for each VPE. By setting this bit, the TLBs will be combined and all entries will be accessible to both VPEs. VPC, or Virtual Processor Configuration, enables the writing of configuration registers that would normally be read-only on a non-MT system. This usage will be noted as I go through those registers. The setting of this bit is only allowed by the TC that is the master virtual processor. I will cover enabling master virtual processor mode when I cover VPE Comp 0 register. eVPE, or Enable Virtual Processing, is set by the eVPE instruction and cleared by the dVPE instruction. If set, all active VPEs on a processor fetch and execute independently. If cleared, only the single instruction stream of the TC that issued the dVPE instruction will execute, thus disabling multiprocessing. The thread that issues these instructions must be the master virtual processor. This bit can also be set or cleared by writing this register. The next two registers provide read-only multi-threading specific configuration information about your core. The TLB shareable bit indicates that TLB sharing amongst all VPEs is possible. This will be set if both VPEs have a TLB. Remember, TLB sharing is enabled by the STLB bit of the MVP control register. The gating storage bit indicates that the processor is configured to support gating storage operations. This is set on reset based on the state of the IT-num entries inter-thread input pins. If the IT-num entries is greater than 0, this bit is set to 1. The programmable cache partitioning bit indicates that the allocation behavior of the ways of the primary instruction and data caches can be controlled via the VPE opt registers IWX and DWX fields. There'll be more information on the VPE opt registers later in this section. The processor TLB enable bit indicates how many TLB pairs are allocatable. The TC's allocatable bit indicates that TCs may be allocated to a VPE through the current VPE field of the TC bind register. Processor VPEs is the total number of VPEs minus 1. The processor TCs is the number of TCs present minus 1. This number can range from 0 to 8. The MVP config1 register contains the remaining core configuration values. The C1M bit indicates the floating point unit of coprocessor 1 implements the MDMX extension to the instruction set. The C1F indicates the floating point unit of coprocessor 1 implements 64-bit instructions. The next three fields, Processor Core Extend, Processor Core Processor 2, and Processor Coprocessor 1, contain information on the number of register set contexts available to each. This number will give you the number of TCs that can use these features in parallel. The following slides show the MT registers that are available to each TC. The TC bind register defines the VPE affiliation and identification of this TC. The TC can read this register to determine which TC it is and which VPE it is associated with. The current TC field is the TC number of this TC. The thread bus error is a status bit that will be set when a load instruction executed from this TC caused a bus error. The current VPE field tells the TC which VPE it belongs to. This field can also be set to associate the TC with another VPE. The TC context register is purely a software read-write register. For example, it could be used by the operating system as a pointer to thread-specific storage. The TC halt register is used to control the fetching of instructions for a thread. Writing a 1 to the halted bit of an activated thread causes the associated thread to cease fetching instructions and to set its TC restart register to the address of the next instruction to be issued. More on the TC restart register later in this section. A 1 in the halted bit also prevents the TC from being allocated and activated by a fork instruction. More on the fork instruction later in this course. Writing a 0 to the halted bit of an active TC allows the associated thread of execution to be scheduled and fetched and executed as indicated by the TC restart register. The TC restart register provides the start address where the thread will start executing instructions from when the halt bit is cleared in the TC halt register. The scheduler feedback register is a per TC feedback value from the scheduler hardware to the software. This interpretation is scheduler implementation dependent. For example, it might encode the number of instructions retired in the instruction stream corresponding to the TC since the last time the value was cleared by software, as is the case in our reference design of the weighted round-robin policy manager. The TC schedule register is a per TC value whose interpretation is scheduler implementation dependent. Our reference design of the weighted round-robin policy manager breaks this register down into two fields. STP, if set, prevents the TC from issuing any instructions. GRP sets the group priority of this TC. I'll talk more about weighted round-robin policy manager in the policy manager section of this course. The TC status register provides information and control fields for the TC. TCU 0 through 3 controls the access of the TC to coprocessor 1, the FPU, or coprocessor 2. This can be used to control the access to a processing element that may not be multi-threaded. For example, if you have an FPU that only has one register set, then only one TC should be allowed to use the FPU at a time. You can control which TC uses the FPU by this field. TMX controls the access to the DSP instructions. You might be asking yourself that since the 34K always contains DSP instructions, why have this bit? But it's there for lazy context switching in an OS. If the TC has no access to the DSP, then the special accumulator registers for the DSP need not be saved. The run state of the TC is a read-only field that can provide you with the current state of the TC. A 0 indicates this TC is running. A 1 indicates it is blocked on a wait. A 2 indicates it is blocked on a yield. And a 3 indicates it is blocked on gating storage. There'll be more information on wait, yield, and gating storage later in this course. The thread stopped in delay slot field is a read-only bit that indicates if the TC was stopped executing an instruction in a delay slot. If this is the case, the TC restart register will contain the address of the branch instruction so that when the TC is restarted, the branch will be reevaluated. The dirty thread bit is set by the hardware whenever an instruction is retired using the associated TC, and on a successful dispatch of a TC via a fork instruction. So if this bit is set, you know the TC has executed, and if you're going to do a context switch, you would need to save the registers. If it wasn't set, no instructions have been executed, so there is no context to save. The TC core extend enable bit is defined the same way as in the status register CEE field. The modification of either registers changes the value of both registers. If the dynamically allocated enable bit is set, the TC is available for a dynamic allocation by a fork instruction. If the activated bit is set, the TC is activated, and when the halt bit is cleared, the TC will fetch instructions. The TKSU field is a duplicate of the status register's KSU field. When either is set, both are modified. If the interrupt exec bit is set, it exempts the TC from handling interrupts. You can use this to control which TC handles interrupts. The TACID field is a duplicate of the entry high register ACID field. A modification of one of these registers affects both of them. Next, I'll show the CP0 registers that are specific for each VPE. The shadow register sets for the 34K use up a TC. This register tells the VPE which TC is being used for which shadow register set. It is recommended that the TCs that will be used as shadow registers be the highest numbered TCs. So if you have 3 sets and 9 TCs, use TCs 6, 7, and 8. Since this is a per VPE register, you must make sure that the donor TC is bound to the VPE that owns this register. The TC must be halted and inactive and not usable by a fork. The VPE Comp 0 register indicates the activation state and privilege level of the VPE. All fields in the VPE Comp 0 register are read-only in normal execution, but the MVP and AVP fields are writable when the MVP bit is set for the VPE performing the modification. The exclusive TC field is set by hardware when execution is restricted within a VPE to a single TC. This is caused by the VPE being in exception mode or thread enable bit being cleared in the VPE control register. Either of these conditions will cause only one thread to be executed. When that happens, this field contains the TC number of the TC eligible to run. XTC can also be written by the MTTR instruction as part of cross VPE initialization. If you want to initialize a VPE so it starts with just one TC running alone. TCS, SCS, DCS, and ICS are read-only bits which tell software which caches are shared with at least one other VPE. The separate bits are for tertiary, secondary, L1, Dcache, and L1 iCache, respectively. There is no way for the 34K core to not share caches, so a 34K core will have DCS and ICS set and will have TCS and SCS bits set if it has an L2 or an L3 cache. Master virtual processor bit must be set before software can touch registers on another VPE or TCs affiliated with it. Virtual processor activated controls the running of any TC attached to a VPE. If this bit is 0, no TCs bound to this VPE can run. This bit can be set by another VPE that is the master virtual processor using the MTTR instruction, which I will go into later in this course. During initialization, it may be necessary for the TC that is running the boot code to initialize the registers of another VPE or TC. There are two things that need to be done to be able to do this. First, set the master virtual processor bit in the VPE CP0 register. Then write the number of the target TC that you wish to initialize. This will cause the MTTR and MFTTR instructions to read and write the target TC's registers. You can also write to the VPE registers that the target TC is bound to. The VPE Conf1 register is instantiated per VPE. It indicates the coprocessor and UDI resources available to the VPE. All fields in the VPE Conf1 register are read-only in normal operation, but they are writable while the MVP control VPC bit is set. With this register, you can restrict the use of these resources to a single VPE. Don't forget, to use these resources by multiple threads, there must be as many contexts of these resources as there are threads that will be using them. The VPE control register controls the behavior of some of the actions that can cause exceptions instead of blocking. The yield scheduler intercept bit controls how the processor will behave when a thread would be blocked as the result of a yield instruction. If set, any thread that would be blocked by a yield instruction would cause a yield scheduler exception. The gating storage intercept bit controls how the processor will behave when a thread would be blocked as a result of the use of a load or store instruction to gating storage. If set, any thread that would be blocked by a gating storage access would cause a gating storage scheduler exception. The exception field encodes the cause of the last thread exception. A 0 indicates a thread underflow on yield. This is caused when the execution of a yield would result in yielding the last thread in the system. A 1 indicates a thread overflow on a fork. This is caused when there is no thread available to fork. A 2 indicates a bad qualifier fed to the yield instruction. The exception happens when bits set in the signal mask given in the RS register of the yield instruction are masked out by the YQ mask register. This would result in a condition that would cause the thread never to be restarted. A 3 is an exception on gating storage operation when the trap bit of the gating storage cell is set, which would cause the processor to take a gating storage exception on any PV or EF access. I'll cover this later in the inter-thread communications section of this course. A 4 indicates the yield scheduler intercept bit was set when a yield instruction would have caused a thread to block. A 5 indicates the gating storage intercept bit was set when a load or store to gating storage was done. The threading enable controls the threading mode of the VPE. If set, multi-threading is enabled for the VPE. If unset, only one TC within the VPE is allowed to issue instructions. Normally, this is set or unset using the DMT or the EMT instructions. More on these instructions later in the course. The target TC field selects the TC number of the other thread context for the MTTR and the MFTR instructions. The VPE op register can control the use of the way of the caches between VPEs. This may help with cache thrashing problems. The instruction way exclusion field controls which way of the instruction cache will be excluded for use by the VPE. The data way exclusion field controls which ways of the data cache will be excluded for use by the VPE. Each bit in the mask corresponds to a cache way, so bit 0 of the mask would exclude way 0, and so forth. The cache partitioning active bit must be set for the masks to take effect. The VPE schedule register is a per VPE value whose interpretation is scheduler implementation dependent. For example, it could encode a description of the overall request issued bandwidth for an associated VPE, or it could encode a priority level. The default policy manager for MIPS is the round-robin policy manager. This policy manager does not use the VPE schedule register. There is an alternative policy manager for MIPS called weighted round-robin. This policy manager uses the VPE schedule register to control if it rotates priorities or uses a strict priority scheme. Our 34K implementation can use the policy manager designed by you and use this register as you see fit. There'll be more information on this topic in the policy manager section of this course. The YQ mask register will enable the bits that can cause a yielded thread to be scheduled. For the 34K, there are 16 hardware pin inputs possible. Setting a bit in the mask field will enable that pin to be part of the decision to unyield a thread. There will be more on the yield interface in the instruction section of this course.